In this notebook, we will first develop an intuition for what a vector is. We will then go through the code for few basic vector operations, often used in machine learning. We will go through adding two vectors, subtracting one vector from another, finding length of a vector, scaling a vector, and lastly, finding the angle between two vectors. We will then look at a simple model that utilizes all these operations. To recap what a vector is like an arrow. It has a length and direction. We represent them in code as a list of numbers. For example, this is a one-dimensional vector, this is a two-dimensional vector, and this is a five-dimensional vector. We can visualize a two-dimensional vector as follows. Imagine we start at the origin and walk 3 steps to the right and 4 steps up. The vector captures how far, and in what direction, we moved away from the origin. The numbers 3 and 4 are often called scalars. They can be positive or negative. For instance, the vector -3, 4 can be visualized as the vector we get by connecting the origin to the point we reach by walking 3 steps to the left and 4 steps up. Even though we cannot visualize any vector more than 3 dimensions, the vector operations we perform in this notebook applies to a vector of any dimension. Let's start with how we can represent vectors in code. These are examples of 1, 2, and 6-dimensional vectors. We will use a standard library to perform vector operations. These are examples of adding and subtracting vectors. Programmatically, they are no different than adding or subtracting numbers. Now let's compute the length of a vector. The length is simply the square root of the sum of squares of the elements of a vector. We can scale a vector, that is, shrink or increase its length, by multiplying every element of the vector by some number. Note the scaling of a vector can change its length and also reverse its direction. We can scale a vector to a unit length vector that points in the same direction as the original vector. This operation is often called normalizing a vector. We will be normalizing vectors when we want to find the angle between two vectors. To find the angle between two vectors, we will make use of an operation called the dot product. The dot product of two vectors, a and b, is the sum of the products of each element of vector a with corresponding element of vector b. Note that vectors a and b have to be the same dimension. The dot product of two vectors collapses the two vectors into a single number. This number tells us if the two vectors are pointing in the same direction or not. If they are pointing in the same direction, the value is positive. If they are pointing in opposite direction, the value is negative. If they are perpendicular to each other, the value is 0. Let's look at a few concrete examples. When the two vectors are roughly pointing in the same direction, the dot product is positive. If the vectors are pointing away from each other, the dot product is negative. If the vectors are at a 90-degree angle to each other, the dot product is 0. In fact, there is a formula that helps us find the exact angle between two vectors using the dot product. The dot product of two vectors a and b is equal to the product of magnitudes of the vectors and the cosine distance of the angle between them. So if we convert both the vectors to unit length vectors and then do a dot product, we get the cosine value of the angle between the vectors. These are the dot products of two normalized vectors. Note, as mentioned earlier, we can do a dot product between vectors of any dimension, so long as their dimensions match. We will now look at a model that leverages all the vector operations we saw above. Word2Vec is a model that takes in as input a text corpus made up of sentences. After training, the model outputs vectors for each unique word in the corpus. These vectors capture semantic similarity between words. For instance, the angle between the words cats and dogs would be smaller than the angle between the words cats and quantum. The model learns this through a simple training procedure. Let's say we decide to represent each word as a 200-dimension vector. At first, all the unique words in the model are assigned a randomly generated vector. Then each sentence in the input corpus is taken, and the vectors for each word is tugged closer to the vectors for other words in the sentence. At the same time, each word in the sentence is also tugged away from few other words not present in the sentence. For instance, consider the sentence, "A dog played in the house." The vector for a is tugged closer to the other words in the sentence. It is also tugged away from few words not occurring in the sentence. The same procedure is repeated for dog, played, etc. Tugging closer here means taking a small component of, say, dog vector and adding it to the vector for a. Tugging away means taking a small component of, say, vector for plane and subtracting it from a. Doing this over and over, for all words in the corpus, yields vectors that are semantically related. In essence, we use vector addition, vector subtraction, and vector scaling during training. Once training is done, we can examine the semantic similarity between vectors. To do this, we normalize each vector, that is converted to unit vectors. Then we can take the vector for any word in the corpus and examine how related it is to other words by doing a dot product between them. So during inference, we use vector scaling and dot products to find angles between vectors. This figure is the output of a word 2-vec model. It shows vectors that are closest to the vector for cats. The second column shows the dot product between the normalized vector for cats and the normalized vectors for the words in the first column. We can see that the model has learned that cats are closely related to other animals. We will now look at answers to frequently asked questions. Is dot product only used for finding angles in machine learning? Dot products are used in machine learning for more than just finding angles. They are a fundamental operation in numerous algorithms. If we consider two vectors, A and B, the dot product helps in determining the projection, or the component of A, in the direction of B. This can be understood with a simple example. Imagine moving a block up an incline, for a distance d. The horizontal distance the block has moved is the dot product of a vector, along the incline, and a unit vector in the horizontal direction. In this use case, the dot product provides a measure of how much one vector extends in the direction of another vector. In the context of artificial neural networks, the weights of a neuron can be viewed as a vector. These weight vectors, learned during training, act as feature detectors on the input. When the dot product of the input and a neuron's weight vector is passed through a function that suppresses negative values, the neuron effectively becomes a feature detector. That is, the neuron produces a non-zero output only when the input contains the feature it is designed to detect. In this use case, the dot product operation acts as a means of feature detection. A collection of neurons forming a neural net layer serves as a set of feature detectors. For instance, consider image pixels flattened into a vector and fed as input to each neuron in the first layer of a neural network. Each neuron, equipped with a vector of weights, serves as a feature detector, with the weights of these vectors being learned from data. In practice, all the weights of all the neurons in a layer are arranged into a matrix, and the input vector is multiplied with this matrix. This matrix multiplication essentially involves multiple dot products, meaning multiple feature detectors are operating on the input simultaneously. Two-dimensional feature detectors, such as convolutional filters used in neural networks, can be conceptualized as performing a dot product operation. This is achieved by flattening both the 2D filter and the corresponding 2D input region into linear arrays. The convolution process then becomes equivalent to taking the dot product of these flattened arrays. Dot products play a key role in the popular neural network architecture known as transformers, particularly in the implementation of the attention mechanism. The attention mechanism enables the model to dynamically focus on the most relevant parts of the input, significantly enhancing its ability to understand and generate language. For example, the vector representing each token in a sentence is constructed as a weighted sum of all tokens in the sentence, where these weights are computed using dot products between the vectors. Additionally, these dot product scores are scaled by the square root of the dimension of the vectors. This scaling step is crucial. It prevents overly large values that could dominate and disrupt the learning process. In essence, using dot products in the attention mechanism, the model effectively assesses the relevance and relationships between different segments of input, which is central to how transformers process information. What is the underlying intuition for the dot product operation capturing alignment of vectors? The intuition behind the dot product operation for capturing directional alignment between vectors is rooted in its computation. That is, multiplying corresponding elements of two vectors and then summing up these products. When corresponding elements in the vectors have the same sign, their product is positive, indicating alignment. Conversely, if the elements have opposite signs, the product is negative, signifying misalignment. If one of the elements is 0, it indicates neither alignment nor misalignment at that position. The magnitude of the dot product reflects the degree of this alignment. The sum of these individual products yields an aggregate measure that reveals whether the vectors are aligned, misaligned, or orthogonal to each other. The magnitudes of individual elements or numbers in a vector play a critical role in neural networks. Elements with extremely large magnitudes can dominate other elements in the dot product computation. To manage this, techniques like regularization are employed to keep the magnitudes of individual elements within a controlled range. This approach ensures that no single element disproportionately influences the dot product calculation. A dominant element would disproportionately affect the dot product output, leading to a scenario where a particular feature becomes overly influential. Regularization mitigates this risk by promoting the development of a more balanced and generalizable model, preventing over-reliance on any single feature. Is there any relationship between dot products and Pearson correlation? Yes, dot product operation is also used in calculating the Pearson correlation. Pearson correlation assesses the linear relationship between two vectors, often referred to as variables in statistics, and assigns a score ranging from -1 to 1. A score of 1 indicates strong positive correlation, 0 indicates no correlation, and -1 indicates strong negative or anti-correlation. This score reflects the extent to which plotting corresponding elements of vectors A and B yields a straight line plot. However, there's a notable difference in how dot products are used in machine learning compared to their role in Pearson correlation. For instance, consider the vectors in the figure. The dot product of these vectors is 16, suggesting that they point in the same general direction. When normalized, their dot product is 0.8, corresponding to an angle of approximately 36.87 degrees between them, indicating a degree of alignment. In contrast, the Pearson correlation between the vectors is -1. This indicates a perfect negative linear correlation, as elements in one vector increase, corresponding elements in the other decrease proportionally. To compute this score, each vector's mean is subtracted from its elements. Also, these mean-adjusted vectors are scaled by their standard deviations. The Pearson correlation coefficient is then calculated as the dot product of these mean-adjusted and standardized vectors. In the case of these vectors, when properly standardized or scaled, the dot product results in a coefficient of -1, indicating a perfect negative linear correlation. In summary, dot products in machine learning are primarily used to capture alignment between two vectors. In contrast, Pearson correlation, through mean adjustment and scaling of vectors, focuses on capturing the linear relationship between the individual elements of two vectors.